years ago. Nowadays, is a PhD student at Harvard, working with Madhu Sudan, and I guess a little bit more, even more coding theoretic perspectives. And she'll be telling about sort of a line of work, in particular, our latest work. What happens when you sort of think about?
Would you like a Madonna?
No. I'm good. Yeah. What happens when you consider a small field? Particular Boolean fields, Boolean circuits, and sort of recent work around that. So take it away, Noor. Actually, maybe do you want this or do you want the Madonna thing? You good?
Okay, so thank you, Ron, and thanks, organizer, for inviting me. So about IOPs, I will not go into. We've heard enough. This is based on works of and a joint work with Noor and my wonderful previous advisor, Ron. Okay, so in this talk, we're going to focus specifically on prover efficiency and in different ways to define prover efficiency in IOPs. So before we get into that, let's just start with what do we know about these things? So the first IOP, or the first PCP, had a prover that ran in exponential time. Then, with some advancements in PCP, specifically with the PCP theorem, the provers started running in polynomial time. Then we had a lot of advancement in specifically IOPs, leading up to provers running in nearly linear time. And now at this point, the distinction between linear and near linear IOPs already highly depends on the exact model we're working with and what exactly are we counting when we say linear. So this talk, we're going to focus on prover efficiency, specifically the prover overhead between computing and proving, in sort of the most strict model of when we say linear versus nonlinear. And we'll talk about minimizing the number of rounds, which can have a lot of practical implications. So the talk overview is going to be the following. We'll start by defining the model, the efficiency measures. Then we'll see a sum-check-based protocol, which will have a quasi-linear prover and a logarithmic number of rounds. And then we'll sort of work our way into reducing the prover complexity and then reducing the number of rounds. Okay, so what is our computational model? So we start by thinking about whatever computation we're trying to work on as a circuit. And let's say the circuit has some size S. So then we want our prover to also be a circuit. And we're asking what's the size of the prover's circuit? So obviously, it has to be at least S, but hopefully it won't be too much more than that. Specifically, we're going to also be focusing on Boolean circuits. So why circuits? Well, we could talk about runtime instead of prover size, which often has a lot of correlation. But then with runtime, we start asking what kind of operations we're allowed and what kind of memory access. So circuits just give us a more sort of clear view where everybody's on the same page. Now, why Boolean circuits? So for a couple of reasons. First of all, some computations just come as a Boolean circuit themselves, for example, like hashing. And then for that, we also want our prover to be a Boolean circuit so that we're not sort of comparing two different things. So just that we compare the same thing, we want them to be Boolean circuits. But also, if we're talking about arithmetic circuits, then we go back to the same question of over what field, right? So you can think of it this way. If I'm saying I can take this wall down in 1 hour, you really should ask me, do it with what? So if I say I can take it down with this small hammer, then it's one thing, but it's much easier to do it with this big hammer. So you can think about it as Boolean circuits versus arithmetic circuits, where the Boolean circuits are like this tiny hammer, and the arithmetic circuits are a bigger hammer the bigger the field gets. So for this talk, we're focusing on computation as a Boolean circuit, a prover as a Boolean circuit, and we will want our prover to be linear in the size of the computation, which is a line of work that started with the Noor first work of this. Now, some of the snarks you might know have a linear prover. So what is so different about this? Well, they have a linear prover, but it's linear in the number of field operations. And they don't really account for the field operations. So here we're also counting these field operations inside our complexity measures. And we will see later on how this makes things a bit more challenging. Maybe not a bit. Okay, so the second thing we care about is the number of rounds. And the reason we care about that is, so usually in IOPs, or the arguments that the IOPs are, or the arguments that are using these IOPs, in each round, a lot of the work can be done in parallel. But between rounds, we can't really do any parallel work because the prover sends a message, and then it waits for the verifier's coins before it can start the second round. But then you can say, okay, we're running fiat Shamir anyways and everything, there's one round, the prover's not waiting for anybody, and we're happy. The problem is that even if there's no verifier, the prover is still simulating the verifier, which means that it still has to hash the function to get the coins, and only then it can start the second round. So either way, with or without fiat Shamir, the number of rounds will have a lot of efficiency implications. Okay, so hopefully now I've convinced you that we care about these two things, being the number of rounds and the proving overhead, specifically in this like Boolean circuit model. So unfortunately, there's some trade-off between the two. So if we have a circuit that is like the original computation is a Boolean circuit of size S, what can we say? So for one round, aka a PCP, we can only get a superlinear prover. In fact, we only even have a superlinear proof size. If we're happy with a constant number of rounds, then we can take down the proof size, the proof length to be linear, but the prover still has to run in superlinear time or size. If we're okay with a much bigger number of rounds, a logarithmic number of rounds, then we can finally have a linear prover. And the question is, if we insist on linear prover, what can we get anything less? Well, what we'll see today is that we even can get a log star number of rounds. You haven't seen log star in a while, I bet. Okay, so finally, we're ready to sort of have a theorem here. So for every nice Boolean circuit of size S, exists an IOP where the prover is linear in the size of the circuit. The verifier runs in polylog time. There are an order of log star number of rounds and an order of log star query complexity. So before we get any further, what is this nice I'm hiding here? So nice, I mean sort of like regular circuits or circuits that have a lot of repetitive structure. You can think of it as like doing some batch computation. So for the protocol we'll see today, we'll have a constant soundness error, but you can get a 2 to the minus lambda soundness error with paying an only polylog overhead, where like the trivial thing of repeating would give you a lambda overhead. Now, if you really want all circuits and not just these nice circuits, then we can also do that, but then we have to pay in a linear verifier preprocessing. And if you really care about the factors I'm hiding inside, then it's like specifically 2 log star plus some constant. So in case you haven't seen log star in a while, this is just the number of times we have to do log over a number to get it to be at most 1. And here are some examples. And why did I put this huge example here? Well, because this is way bigger than the number of atoms in the universe. So really, you can think of log star as just being bounded by 5. Okay, so we'll start with some more technical things. So any questions before that? Right, right, yes. Or for all I know. Okay, so our key ingredient is going to be an IOP for inner product. And I guess we've seen inner product come up, so maybe this doesn't surprise you too much. So what do I mean by that? Given X and Y, we want to prove that their inner product is some value. Now, the verifier can just go ahead, read them both, multiply every index, sum up, and do everything. But we want the verifier to run in sublinear time. And the verifier has oracle access to some encoding of X and Y. And what do I mean by encoding? We'll get to that later, but we've also seen error correction codes already, so this is what we mean. And why is this useful? Well, if we have that, if we have a linear prover that can prove this, then we can get a linear prover for rank 1 constraint satisfaction, which will give us IOPs for nice, or for specific rank 1 constraint satisfactions, which give IOP for nice NP. Okay, so proof outline. Inner product check really, really sound like sum check. So let's go ahead and do that. And I won't get much into sum check, but let's kind of see why this is useful. So what is sum check? We have some low degree polynomial over some field. with m variables, and we want to prove that the sum of this polynomial over the n-dimensional Boolean cube is some value. So the protocol that does sum check has this, where V has oracle access to the polynomial, and at the end, V only queries one point in the polynomial. So why is this really useful to us? Well, we have our two strings that we want to run the inner product on. We can turn them into functions. So this, I'm just going to be moving between these strings and functions, but really they're the same thing. The only thing that we kind of want to remember here is that when I'm moving from this to this, that m is just going to be log n, which is going to come up later. And then instead of looking at these functions, we'll look at the polynomials that are multilinear extensions over f of these functions. So we've also seen this, but just quickly to say what this means. So we want these polynomials that evaluate over in the entire field, but specifically on the Boolean cube, they agree with f and g. And because here for f and g, every variable has only two values we care about, then we can get these polynomials being multilinear. And finally, we can multiply these two polynomials. If they're multilinear, their multiplication will be a low-degree polynomial, and we can just run some check on that. Sounds very promising, but there are a few problems with this approach. So the first problem is that really the trivial way sort of to run some check only does not give us a linear prover. And again, by linear, I mean as a Boolean circuit. The second problem is that for the sumcheck protocol, we need V to have oracle access to Q. Now, one way to do this would be just that before we even start the protocol, the prover will encode the polynomial and send it, but this also has too much complexity. The prover doesn't have enough time to do this. So that's our second problem. And our third problem is, remember when we said that m is just going to be log n, so these polynomials will have m variables, which is log n, and the round complexity of the sumcheck protocol depends on the number of variables, which means that we will have a log n round complexity, and I promised you log star. So these are our three problems, and for the rest of the talk, we'll sort of tackle them one by one. Any questions about this? Okay, so let's start with the prover complexity of sumcheck, and you're probably used to thinking that sumcheck has a linear prover complexity, so let's understand why in this model it doesn't, and then how we solve this. Okay, so we know what the sumcheck protocol does, and let's sort of just a bit get into how it works, and we want to keep in mind two things, the prover complexity and the soundness, which we'll analyze later on. So how does the sumcheck work? We have this polynomial that we want to evaluate over the Boolean cube. So the prover goes ahead and evaluates basically almost everything. So it keeps the first variable as a variable, but then it iterates over all the other variables for all the values, sums up everything, and sends this new polynomial to the verifier. Now the prover has done most of the work. So all the verifier needs to do is sum up q1 of 0 and q1 of 1 and make sure that it's this value. But also, it doesn't really trust the prover, so it wants to check that q is the right polynomial. Now, if the prover sends a wrong polynomial, then these two polynomials are different, so they disagree on a lot of points. So if the verifier just checks one point, with high probability, it would cache a bad computation. So the verifier can just choose one point it wants to check. So let's say the verifier wants to check q1 of R1. Well, what is that? What is q1 of R1? It's basically fixing the first variable, but then summing up over everything else. So if we do that, then we just have two polynomials with m-1 variables, and we're back to our original problem. But that's fine, because we've reduced the number of variables, so they can just do the same thing and recurse. So they do the same thing, eventually leading up to the verifier wants to query this one polynomial in Rm, but this is basically the first polynomial at R1, R2 to Rm. Okay, but now it has queries to f and g, multiplies the two things, checks, and everything's fine. Okay, so we want to talk about the prover complexity versus soundness here. So we saw what happens at round 1, but at round t, the same thing basically happens. So at round t, we've already fixed the t-1 first variables. The tth variable stays as a variable of that polynomial, and then we sum up over everything else. So For the m minus t variables, we basically have to give them all like 0, 1 possible evaluations and sum up over everything and multiply and so on. So we have something like order of 2 to the minus t field operations. Now, I'm kind of here ignoring the fact that the prover is going to also have to evaluate these polynomials. The prover doesn't have access to the polynomials, it only has access to the functions. So at some point, it needs to extend them to polynomials. But I can demonstrate the issue without accounting for this. And also, this is not a big cost here, but keep that in mind for later. So we have 2 to the m minus t field operations, which means this is per round, which means that this is the sum. Now, this thing converges to 2 to the m. And remember, 2 to the m is just our n, so it's linear. So it seems that everything is linear and we're happy. Only this is linear number of field operations. So this looks more like this. Okay, but not all hope is lost. If our field is a constant size, then this still converges to 2 to the m, and everything's fine. Okay, but what about soundness? So where is our soundness coming from? So at every step, the verifier is checking these polynomials. And we said that if they're two different polynomials, then they can only agree on a small number of points. So the soundness error is coming from me choosing the specific point that they coincidentally agree on. But how many points can there be? Well, there can be d points, which is the degree, over the number of fields. So this happens every round. And if we accumulate this error for all rounds, this is m times d over f. Now m is just log n, which means that if the field is a constant size field, this is meaningless. So to have any meaningful soundness, we need the field size to be at least m, which is at least log n, which then means we will be paying something like log n. So not linear, right? Okay, so if you were happy with arithmetic circuits over some large fields, then the sum check is linear and we're done and we're happy. But we promised Boolean circuits, so we're not done. So we have these two constraints and they're kind of colliding, right? Like if we want good soundness, we have to choose big fields. If we want good good prover complexity, we have to choose constant fields. So it seems that really we can't get the best of both worlds. So what do we do at times of conflict? We compromise. We start with a small field, and then we have the fields grow bigger. So why does this help? So the thing about the sum check protocol is that at every round, the prover is working on a smaller problem. Or if you remember, if you just look at this sum, the number of operations on the field it has to do in every round gets smaller and smaller, which means that at every round, we can afford to do our operations with bigger fields. And for soundness, this is also fine. If we start with a field big enough, a constant, but big enough, we can sort of also grow these things nicely. So any choice of something of the order of these fields should work and satisfy the two constraints. But we'll see later on for the log star stuff that we need something more specific. Okay, great. So any questions about this part? Okay, so we've solved the issue of the prover of the sum check protocol. But now, so the prover ran in as a linear Boolean circuit, and we're happy. But at this stage, the verifier wants to check one point in the polynomial. And we said that sending the polynomial is too expensive for the prover. So the verifier doesn't have access to this polynomial. So this is a problem. And in order to solve that, we kind of have to take a detour into error correcting codes. So we talked, previous talks have mentioned error correcting codes, but we kind of want a specific perspective. So let's go ahead and define these things. So what are error correcting codes and why are they useful? So they come up in a very different setting. In a setting where we have Alice that wants to send Bob some message. But they're sending it over a very noisy channel, or well, not very noisy, but slightly noisy channel, where some of the bits can be flipped. And so then Bob won't know what Alice wanted to say. So instead of just sending the message, Alice will send some function over the message. And we call this function a code, where this function takes a string of size k and outputs a string of size n. And the property we want is that if we look at two messages, then their code words are going to be very much far apart. And by far apart, I just mean that they don't disagree on a lot of the points. And why is that helpful for us? Well, if they don't disagree on a lot of the points, and a small number of points are flipped, then Bob would still understand which original message this was coming from, and would still be able to sort of correct and understand the message. So one thing we really care about in codes is the distance, and the distance is just the minimum over all two pairs of code words of what I just said, which is like the number of disagreement points. So the bigger the distance, the better. Another thing we really care about with codes is the rate. So the rate, you can think of it basically as like how many messages, how many bits of symbols of information I intended to send over the number I actually end up sending. So we want these two to be as close as possible. And finally, we care about encoding complexity, which is how long it takes Alice to like compute the code word of her message. So one example is multilinear extensions. These are codes, and the way to think about them as codes is that we have a message. So the code word would be the polynomial that agrees with this message on the Boolean cube. And the distance for these codes follows from the fact that two polynomials of low degree cannot agree on a lot of points. So back to our proof setting, and why is all of this helpful? Well, we can think of our messages as sort of computation, like a computation that the prover is doing. And so if the prover sends the code words of these computation, and the verifier is trying to figure out whether the computation is right or wrong, then if we have the wrong computation, the code word of the wrong computation is very far apart from the code word of the right computation, which means that just checking a small number of bits in that computation would help the verifier understand if it's the right or wrong computation. And if there's a mistake, with high probability, it will still catch the mistake, even if it doesn't read the entire thing. So from that, it's obvious that the distance of the code is going to relate to our soundness. The rate usually relates to our proof length, and the encoding complexity is just the prover's work. So it's going to be relating to the prover complexity. So why is all of this helpful for us? So turns out there's nothing really special about polynomials, and we can run some check on any tensor linear code. So what do I mean, tensor linear code? So linear code, and I feel like I might confuse you here. Now, this is not runtime, not complexity, not nothing. It's just the fact that the map of that code is a linear map. And tensor, it doesn't really matter, but it just has like a nice structure. But almost all of the codes we think about are linear codes, and if you give me a linear code, I can construct a tensor code out of it. So we have these codes, and we're happy. So what do I mean when I say we can just run some check on them? So I mean that if we have a message that we want to sum up, we want to like prove the sum of, then we can do something very similar to the sum check protocol, where at the beginning, P sends the code of this message, and then they run something like sum check, and at the end, instead of querying a point in a polynomial, the verifier queries a point in the code of that message. And basically, in the run, everything, like they're not sending polynomials, they're sending code words. And so instead of having this notion of two polynomials can't agree on a lot of points, we have this notion here of two codes cannot agree on a lot of points. But everything else works out basically the same way. So why is this helpful for us? Because although polynomials cannot be encoded in linear time, which means that given a message, we cannot write the entire polynomial in linear time, other codes can. So let's try a second attempt at this. So we have our x and y, and now we convert them into code words, ex and ey, and the prover now can just do this with linear time and send out the code words to the verifier. And we use a linear time encodable code. We know that these exist and are linear, and everything's linear as a map, and we're happy. And then they just run sum check on ex, pointwise multiplication, ey. Don't take a picture yet. This is not going to work. Okay. So what is the problem with this? Oh, and at the end, V queries the points, whatever.
This sum check is not that sum check, right? It's the sum check from before?
It's this sum check. I mean, it's the same sum check as before. Sorry, it's the same sum check as here, which is on this new code that we have. Only the problem is that this might not be a code word. So I said nothing is special about polynomials. In fact, there is something special about polynomials. And what's special about polynomials is that if you multiply two polynomials, you get a polynomial. And if we think of polynomials as codes, then if we take two messages and pointwise multiply them, and we take their two code words and pointwise multiply them, something nice happens. This is not true for every code. And we don't know of any linear time encodable code that has this nice property. So if we had this linear time encodable code that has this property where we can just multiply the two code words and then run some check on them, then everything would be nice, but we don't. Does this answer your question? Okay, great. Okay, so once again, we have a problem. We have two nice codes. Each of them has one nice property, but we kind of want to get the best of both worlds and mix these two properties. Any ideas come to mind that possibly we've heard about twice today? So we do code switching, which is basically getting the best of both worlds. Okay, so now this is really the proof outline. So we have a claim on some inner product of x and y, and then we run some check. Now back to our normal sum check, polynomials, everything's fine. And then at the end, the verifier wants to check one point in the multilinear extension of x and y. So instead of doing that, it just produces a claims on these things, so this part is basically an interactive oracle reduction, right? Okay, so it wants to now prove claim, or it wants to be convinced of these two claims on x and y. And now we do code switching, which is basically generalized sum check. It's sum check with some coefficients. And instead of that, at the end of it, the verifier will check 2 points in the encodings of x and y. Okay, so I said before, we can't really run sum check on these, like the way we wanted to run sum check on these new codes doesn't work, and now I'm telling you we want to run something that's even more general than sum check. So what's happening here? So why did we even bother with the first part? So the really nice thing about the first part, it sort of separates the claims about x and y. So what we gain in the first part is that now we have a claim on x and a claim on y, and they're separate. And so now we can use this nice code that might not be multiplicative. And we're running what they need here is one single point of the multilinear extension of x and y. Okay, so the first part we've seen how to do, right? So now I only owe you the second part. Questions about this? Okay, great. So eventually the first part is going to take log star rounds, and the second part will just be a constant number of rounds. But why is it log star? Right, exactly. Great question. So it's not yet. It's now the first part we only saw log n rounds. Okay, so for the second part, you can think of it just as a polynomial commitment scheme. So if we look at this entire thing, basically the prover starts by sending this like encoding of x and y, and you can think of it as a commitment to some polynomial. And at the end, where the verifier wants to query some point of this polynomial, we can think of the second part as just like opening one point in that commitment. Okay, so finally we can get our theorem about specifically IOPs. So we have x and y, where P has access to x and y, V has oracle access to EX and EY for some linear time encodable code E. And then we have an IOP proving the inner product such that this we've seen, the prover is linear, they're in order of log star rounds, log star query complexity. Oh, sorry. Okay, so for now, let's start with this part, which is just the log n. So for the log n, we had an outline where we do first a reduction, do some claim on the MLE. This part we've seen, and then from MLE to the second code. How am I doing on time? Okay. So this part is a previous result of Ron and Noga. But the protocol we saw, or the outline for the protocol we saw, is actually much simpler. So in the first result that achieved this, they did code switching after every round of sum check. So you do one round of sum check, code switch, one round of sum check, code switch. And the protocol we saw just does the entire sum check and only one round of switching at the end. And it will be really useful for our log star round, so that's why I showed it. Okay, so this half we saw. Let's talk about the second half. And okay, yeah, I think we're fine with time. So we want to do code switching. So let's have this more specific. So we have some function f, where p has access to f, and v has oracle access to the encoding of f. Then there's an IOP for proving some point of the MLE, right? This is what we want. It's for a nice point, such that the prover is linear. There's constant number of rounds, constant query complexity. So what is this nice point? Yeah, so this just means that the point is coming from these growing fields. So this is weaker than if I didn't say nice point, but we don't mind much because we know that our first reduction is going to anyways produce this nice point, so we can just use this one.
Sorry, what exactly is the definition of nice point?
Okay, great question. Yeah, so the definition is just that it's coming from these growing fields that satisfy the two soundness and complexity constraints we saw before. There are a few fields that we can choose different types of growing fields that satisfy this, and so any of them is a nice point.
Maybe first thing, what is a not nice point, and then it will help clarify.
Okay, so a not nice point is if we have that, so this point has like R1, R2 to Rm. So a not nice points would be all of these things coming from a constant field, because then we don't have any soundness. Or a not nice point would be that all of these points are coming from a non-constant field, because then the prover complexity would be too big. So a nice point is kind of starting with the constant size field and then growing so that we have a balance between the soundness and the prover complexity. Great. Any more questions? Okay. So turns out it's not even trivial to compute a single point in the MLE with linear time. So, let alone proving. So why is this still possible? So the way this is done is that we sort of extend the polynomial one variable at a time. So we can think of it the following way. One point in the MLE is just linear combination of the original function, right? But it's a linear combination with really nice coefficients that have a very nice structure, which allows us to sort of, if you recall how we define these with this, I think we saw the equation before. It was equality and so on. So there's a very nice structure of these coefficients, which means if we extend our polynomial one variable at a time, and then sort of reuse the work we did in the previous round, and use one more fact, which is that we have these nice points that are coming from these growing fields, then with all of these together, we can still get the linear prover. Okay. So the proving part is very similar to computing. So basically, we can think of it this way. In SumCheck, what we're doing is that we have a message and we want to compute the sum of all of its elements. Here, we have something similar. We have our message and we want to compute a point in the MLE, which is a linear combination of these things. But it's not any linear combination. It's a linear combination that has a very special structure of the coefficients. So when I said we can do SumCheck on any other code, basically what we're doing here is that we're doing something very similar to SumCheck on this new linear code that we have. Okay. Any questions about this? Okay, great. Okay, so the two things we wanted in the beginning, we did. One last thing that I didn't tell you what to do is how to reduce from log rounds to log star. So let's kind of remember where is this log coming from. So we started with our string, and then we turned it into a function, which was on 0, 1 to the m, And we said that, okay, in this case, m is log n, and sumcheck has the m rounds. And this is where the bad rounds coming from. Okay, but we don't really have to use this specific type of structure of function, right? We can use any function. We can use a function that looks like this, where HIs are just any subset of the field. Okay. So ideally, we want our L to be a constant. To make our L a constant, then HI would be something like n to the 1 over L. So one problem is that we cannot, the sort of the polynomial that agrees with this thing is no longer a multilinear polynomial, because the reason we were able to have multilinear polynomials is that every variable had two optional values. So here every variable has n to the 1 over L values, so we can't do multilinear. But that's not really a problem. We can do low degree extensions and everything, and like sumcheck works on low degree, and everything is fine. So that's not an issue. The other issue is that even in the first round, the prover size, because of like sort of this extending like the function, has this complexity. But this is if we do it in the trivial way. So if we do it in a slightly smarter way using FFTs, then we can get, for the first round or all of the rounds, n times polylog n. Not too bad, but I promised you really a linear prover. So still not good enough. So this is why we can't get constant. And so once again, we have this problem. If HIs are like constant size, then we can get the prover to behave nicely. But if the HIs are not a constant size, then we can get a constant number of rounds. So we have this trade-off between rounds to linear prover. But you've seen this before. So what do? Yeah, we start with a small HI and then we grow them. Okay, so this time I will not write the constraints because they're too ugly, but I will just tell you the following. So remember where we had, I'll go back. We had this n polylog n. And so this means that at every round, sort of, this is what we're extra paying, which is why between every round, this is the growth that we can have. So this 2 to the HI minus 1 kind of translates to this, comes from this polylog n. So this is the way these things grow. And then what is L if this is the growth? Exactly, it's log star. Now, it's not really log star because these don't grow so nicely. 2 to the, so it's like 2 over something. So this is why we get 2 log star and not log star. But basically, this is the idea. Great. Any questions?
Maybe we conjecture that it's 1 plus a little bit log star.
Right. Yes. Don't still let me finish my thesis without without that part. Okay. Great. So our main result. All right. Never mind. Was IOP for regular Boolean circuits, where prover size is linear, and we have log star. So the open questions were, can we get the same result for all circuits, and not for these just like regular circuits? So we said yes, but then we pay in verifier time. So can we do this without paying in verifier time? The second question is, can we get this with a constant round IOP with a linear prover? And we don't know that this is true even for arithmetic circuits over large fields and not just Boolean circuits. So one way to solve this question would be to have these codes that do it all, that are both have this multiplication property and have this linear encoding time. So if we had these codes, we can get, even in Boolean circuits, the constant number of rounds and the linear overhead for the prover, but we don't know if these codes exist. Possibly with other directions, you could also do that. Okay. Yeah, so thank you very much for listening, and I'm happy to answer questions. Right, so, okay. Hopefully I have the right statement of theorem. Okay, never mind. So for every circuit, there exists a prover and verifier. So the circuit is sort of encoded inside the prover and the verifier.
If you're asking for the verifier's perspective, then think of offline preprocessing that reads the entire circuit, stores only an oracle or whatever, and then online your small.
So what's the difference? Like, why is this nice? Got to do that here also, or?
This is a different nice. There's
like the previous.
Okay, the previous nice.
Yeah.
So say again, what is the notion of niceness, or?
I think why couldn't you just do this, pre-processing with the existing IOP?
Essentially, there's a problem in the lin check, the lin check of a Boolean field. Yeah. So you need some structure.
So, linear codes are not multiplicative codes are not linear. I understand correctly.
Well, I mean, we don't know of any codes that are, but we don't know that there can't be a code that is both things.
So what's the obstacle there? Do we understand what the obstacle is? We don't know.
Maybe I can add that, so linear codes are a dime a dozen. Multiplicative codes are very rare, and they're sort of coming from algebra, essentially either polynomials or fancier versions like AG codes. And the number of multiplicative codes that we know, especially efficient, are basically polynomials or AG codes. So we don't have, that's sort of a structural challenge.
And what about the round-the-robin soundness?
Here, yeah, this should have right, basically all we're doing is sum check.
But maybe, so I think Noor was focusing on the constant soundness regime anyway, so it's not super relevant. I think she mentioned that there's a work by myself and Justin Harmgren, which upgrades the soundness at better cost than repetition. And you can also ask here what happens with repetition. One observation sort of is that you might say, here we have a constant error, in the first round in particular, we won't have better than constant round-by-round soundness error in the first round. Even without the fancy thing with Justin, if you repeat, you seem to run into a problem. But actually, if you think of it, it's kind of okay to have constant round-by-round, when you do repetition, you have constant soundness error in the first round, but then it's gradually reducing. So if you think you do lambda forward repetitions, in the first round, half will die. Next round, only half of the remaining will die, and so on. So, yeah, we can discuss more offline. More questions for Noor?
I'm just curious about state-of-the-art theory. Do we give a complete round complexity? Say I want a 2-round IOP. What's the best that we know in terms of prover size and all?
Do you care about verifier size?
Sure. I guess that's a good thing.
I think all of the concretely efficient things are either running sum check or fry or a combination. So all of them have log n rounds hiding somewhere. And in particular, the cost of running stuff like this is that you need to send kind of multiple largish oracles. Doesn't seem like maybe the best idea in practice. Please.
So can you have kind of a hybrid that doesn't actually get you log star asymptotically, but you kind of, so there's the HI are increasing, but then you have a cutoff so that you're not using one for the 2 line. Do you see what I mean?
Yeah, I think as a matter of fact, we do have a cutoff that the HI is at some point, it's the exponential growth you can only do, and at some point we do have a cutoff.
So the reason is that when you don't have a cutoff, the last notch is very, very long, and so.
Yeah. So once you get to sort of polynomialish size, then you want to kind of end it there, because from here on it's only going to be a constant number of rounds anyway.
I see. So you don't actually want them to increase exponentially.
You want them to increase exponentially up till you get to say square root n or something, or n to the epsilon, and then from there on just keep it at n to the epsilon and do 1 over epsilon rounds. Yeah. Great questions. Okay, so let's thank Noor again.
And we'll be back here in 20 minutes at 10 past 4.